Today we will be discussing the topic of gyroscopes. A gyroscope is a wheel with most of its mass along the outermost rim that under ordinary circumstances acts like any other object until it starts to spin, which causes the system to conserve angular momentum, making it resist motion along some axes. A torque increases the angular momentum of a system in the direction of the torque. Torque is equal to the force applied to the rotating body times its distance from the center point of that rotating body. In this demonstration, the green arrow shows the force applied and the blue arrow shows the distance from the center point. To find the direction of the torque, we use a right-hand rule. As shown in the demonstration, you point your fingers of your right hand in the direction of the radius, and you curl your fingers towards the direction of the force. Your thumb will show you the direction of the torque and the angular momentum. This basically says that the torque is perpendicular to the force applied to the rotating body. As you add torque to the system, there is an increase in angular momentum within the system. As you can see, as he speeds up the rotation of the wheel, it gains more and more angular momentum. This system is made by suspending a wheel by one side, so there are more than one torques acting upon the system. There is also a torque between the force of gravity and the distance between the center of mass and the point the wheel is attached to, as shown. This torque causes the wheel to rotate down towards Earth. He shows this repeatedly by dropping the wheel. Now what will happen when we combine these torques? Will the wheel rotate downwards towards Earth, or will it act as a gyroscope and resist the falling action and instead start to rotate around the string? This video is about gyroscopes, so I hope you guessed right. This is a very basic demonstration that displays the capabilities of a gyroscope and how torque and angular momentum causes very special resistance to motion. Let's put this theory to the test. It's time for a brief history lesson. In 1852, Jean-Bernard Léon Foucault first uses the name gyroscope and is credited with the invention. But gyroscopes had been used by European sailors for centuries. For example, in 1743, the Dzierzon's speculum sextant was used to find the horizon on cloudy and misty days when it wasn't visible. Gyroscopes made this possible because they resist the rocking of the boat. A gyroscope works by storing a lot of energy, angular momentum, and inertia because of its motion. All of these stored components help it correct itself when it is bumped off its usual course. In a uniform disk which is rotating around an axis, or a gyroscope, with an angular velocity has an angular momentum represented by c equals I times W times omega, with c being the gyroscopic couples force, I being inertia, W being the angular velocity of the rotating axis, and omega being the angular velocity of the gyroscope about the axis it's rotating around. Alright, great. We have figured out that gyroscopes have a stabilizing ability, but what is the point? How is this useful? Gyroscopes are used in boats, airplanes, virtual reality, video games, smartphones, trains, computer mouses, compasses, military applications, and robotics. Basically anything that needs to stay upright probably has some type of gyroscope in it. Gyroscopes have made us able to make cargo freighters like the MSC Oscar, which is 400 meters long and weighs nearly 200,000 tons when fully loaded. But what happens when a large crosswind comes along and begins to rock the boat? Instead of capsizing, some ships have massive gyroscopes built inside of them to stabilize them from rogue waves and crosswinds. Picture this, you're on a plane with no gyroscopes. You can't tell east from west because there's no compass. Your panic over the direction you are heading is merely increased by the constant shaking and miserable turbulence because the stabilizing system is gone. Then, when you veer hard right to avoid the mountain you weren't expecting, you can't stabilize the plane to an upright position, so you spiral out of control and crash. A tiny bit of exaggeration, but you get the idea. Planes rely on gyro compasses to figure out which direction they're going, and gyroscopes to stabilize them during flight. Gyroscopes' motion is very predictable and able to be tracked. This quality of gyroscopes is used in virtual reality and gaming consoles like the Wii. It uses variation of the gyroscope's position to track the player's movement. The military uses gyroscopes often. They are used in remote control flying of drones for reconnaissance. They are also used in missile guidance for long-range attacks and the stabilization of weapons which are mounted to rugged land or air vehicles. Gyroscopes have made their way into robotics labs. Here is an example of a robot that uses gyroscopes to move around. It's pretty amazing.
The Cubely takes its name from a combination of the English word cube and the Swiss German diminutive Li, indicating something of small size. With a side length of 15 centimeters, it mainly consists of 3 reaction wheels, each attached to a brushless DC motor, motor controllers, inertial sensors, an embedded processor, and batteries. Inertial sensor measurements are fused to get an estimate of the tilt and angular velocity of the Cubely, and the Hall sensors provide the angular velocity of the reaction wheels. Based on these estimates, a nonlinear controller is used to balance the Cubely on its corner, while the angular velocity of the reaction wheels is kept close to zero. Although this method of using reaction torques is similar to the one that is used to stabilize satellites in space, due to gravity, the algorithms used here are very different. With this setup, the Cubely can robustly balance around its corner while rejecting disturbances. Rotate while balancing, and balance on its edge. In addition, the momentum wheels can rotate at very high angular velocities and build up sufficient angular momentum. A rapid braking of the wheel allows it to transfer the angular momentum to the Cubely's body. This allows the Cubely to jump up from a resting position to a balancing position without external support. Balancing on a corner is achieved through 2 subsequent jump-up maneuvers. The first maneuver raises a Cubely from one of its faces so that it balances along one of its edges, and the second raises it from its edge to one of its corners. In addition to balancing, the motor torques can be used to achieve a controlled fall, such that the Cubely can be commanded to fall in a specific direction. Combining these 3 abilities, jumping up, balancing, and controlled falling, allows the Cubely to walk across a surface. Some researchers hope to use this method of locomotion for planetary exploration, while others are using it for self-assembling robots. But for us, it is just a cool little cube that can jump up, balance, and walk.